Chapter 6, Sample Problem Number 2. In both cases shown, a block is moving to the right across a rough table with a constant speed of 2 meters per second. The tables and the blocks are identical. In case A, the block is pushed with a stick, and in case B, the block is pulled with a string. The angle that the applied force makes to the horizontal is the same in both cases. Will the magnitude of the force on the block by the stick in case A be greater than, or less than, or equal to the tension on the block by the string in case B? So a couple of important, really important numbers to pull out or things to recognize. One, it is a rough table, which means there's friction. Second, it's moving with constant speed, which means the acceleration in both cases is 0, right? So we have that there is friction. Oops. But we also have that the velocity is constant, which implies the acceleration is 0, which implies the net force is also 0 in both cases. So there's no net force on this. Okay, what does that mean? Well, if we draw our free body diagram for this guy, we have, of course, a weight, and that's balanced by a normal force, which we're going to call FNA. Notice since the block's identical, I don't actually have to identify the weight. It'll be the same in both cases. And then we have F coming down like this. And that's it. Well, no, sorry. And, of course, a frictional force, which we're going to call FFA. And then the other case B, we'll call that one. Well, case B has the same weight. It has a normal, but we don't know that it's the same force as the normal. It has a frictional force, and we don't really know it's the same force for the friction. And then there is the tension pulling this way. You'll notice that I'm going to rename a bunch of these guys. I'm going to call F sub P our pushing force, and F sub T our tension force. This is my own little tick where I just like forces to have the letter F in their name. Not a big deal, but all right. And what we know here is that all of the forces are the same. All the net forces are 0 in both cases. So I'm going to take FP, this guy, and I'm going to break it up into its components. So I'm going to say, let's get rid of FP. Actually, in fact, what I'll do instead is let's write FP in a nice, relatively faint color. And then remind us that that means it really comes that there is an FPX pushing this way, and there's an FPY, and it's pushing downward. And then likewise, let's erase FP, or FT, and I'll draw it in faint just so, again, you can see what's going on here. That's FT. But instead, what we'll have going on here is that FTX pulls to the right, just like FPX, but FTY pulls up. Instead of pushing into the table, it lifts it a little bit. Why is that important? Well, if we go over here, we can say that from our diagram, the net force in the Y is going to be, well, we have FNA pushing up, we have FPY pushing down, and we have FG pulling down. And that has to equal the sum of the forces from second law, which is the mass times the acceleration, but we know that that's 0. Putting all that together, FNA has to be FG plus FPY. In other words, it's somewhat larger than the weight. But looking over in case B, we would have that FNB plus FTY minus FG, that's the sum of the forces from the diagram, has to be MA, which is still 0. So FNB equals FG minus FTY. Why is that important? Well, it says that the normal force is lesser in case B. right? The normal force is less here than it is here. But if the normal force is less here than it is here, then the frictional force is also less because of our relation between frictional forces and normal forces. Specifically, we know that the frictional force is going to equal mu times the normal force in both cases. So that if the normal force is lesser in case B, then the frictional force is lesser in case B, meaning that we have something like that FFB must be less than FFA. And you still might wonder, well, why does that matter? But now we're going to turn our attention to the horizontal forces. In case A, the sum of the forces in the x direction from our diagram is just FPX minus FFA. Oops. And that has to equal the mass times the acceleration in the x direction, which is 0, which tells us that FPX has to equal FFA. Likewise, over here, we'd have that FTX minus FFB is MA, which is 0. So FTX equals FFB. Wow, well, we're almost there, but now we're going to have to come and look at any more room, and I don't need the free body diagrams anymore. What I have just discovered is that since FFB is less than FFA, then FTX is less than FPX. Okay, almost there now, because from the trigonometry, if we look over here, like for FT versus theta versus the thing I want, FTX, we find that FTX over FT equals cosine theta. So FTX is just FT cos theta. Hopefully that's getting kind of familiar. We've done that a lot of times now. So we'll have FT cos theta here. And then likewise, from our other diagram, we have FP. And we want FPX. And that's theta. And so we see again that FPX over FP is also cos theta. So FPX is FP cos theta. And we don't know much about cos theta, but it certainly isn't 0 in this case. So we can divide it out, and we're left with that the tension force is less than the pushing force. Going back up here, we want to say, is the case in case A, the force in case A is greater than the tension in case B. That was a bit long and drawn out. Let's recap what's going on here. That hopefully will make it easier to remember. What we have here is that the normal force in B is less than the normal force in A, which means the frictional force in B is less than the frictional force in A, which means that the component along the horizontal in B is less than the component along the horizontal in A, which means the total, since the angles are the same, it means the total has to be less in B than it is in A. Or to put it in really, really short form, we are lifting the box, reducing its friction, making it easier to pull. That's what's going on there.